A rare visitor from beyond our solar system is swinging by, and astronomers around the world are watching closely. 3I Atlas just passed its closest point to the sun.
When the Atlas Comet Survey Telescope first detected the brilliant streak of comet C2019 Y4 Atlas several years ago, astronomers were fascinated by its brightness and rapid increase in luminosity. But as the years passed, new technology, refined models, and continued monitoring by NASA's heliophysics and astrophysics divisions have revealed something extraordinary. A previously unidentified anomaly observed as the Atlas remnant approached its most recent perihelion. The revelation has stirred scientific intrigue, as the anomaly appears to challenge existing models of solar-comet interactions, material physics under extreme solar radiation, and perhaps even our understanding of how primordial bodies behave in the inner solar system. Before we start, hit the like and subscribe buttons for more exclusive news. As Atlas made its close approach to the Sun, its perihelion, it became a laboratory for studying the volatile interplay between solar energy, outgassing materials, and electromagnetic fields. NASA's instruments, particularly the Solar and Heliospheric Observatory, SOHO, and Solar Terrestrial Relations Observatory, STEREO, tracked the event with precision. The anomaly first appeared as a series of fluctuating plasma emissions and irregular brightness patterns that could not be reconciled with conventional explanations such as rotational fragmentation, sublimation surges, or dust ejection. What NASA scientists observed was a rhythmic pulse in the comet's light curve, suggesting an underlying process not entirely governed by thermal dynamics or gravitational stress. Data transmitted from Atlas's observation campaign indicated that the comet's nucleus, or what remained of it after earlier fragmentation, was interacting with the solar wind in a highly structured asymmetric fashion. Instead of the expected chaotic shedding of material, sensors picked up coherent oscillations in charged particles extending along the comet's ion tail. This pattern suggested the presence of magnetic field interactions far stronger and more organized than typically seen in small-body comets. The discovery sparked immediate curiosity, for it hinted that Atlas might possess residual magnetic properties inherited from its formation epoch, something that had long been theorized but never definitively observed. NASA's plasma physicists began to model the event in real time, combining heliospheric data with magnetohydrodynamic simulations. The models predicted that if the nucleus retained a ferromagnetic core, even a weak one, the extreme solar proximity during perihelion could induce magnetic resonance effects. These effects might momentarily align and then destabilize charged dust particles, creating a pattern of plasma pulses detectable from Earth. The rhythmic flicker observed by Atlas's monitoring arrays perfectly matched such a prediction. What made it truly fascinating was that the oscillations remained synchronized over a period of several hours, suggesting a sustained resonance rather than a transient burst. If validated, this would mark the first time a small cometary body exhibited magnetically coherent behavior during perihelion, an observation that could reshape existing theories about the role of magnetism in early solar system accretion. Researchers have long debated whether magnetic fields influence the clustering of dust and rock in the protoplanetary disk. Evidence from meteorites shows remnant magnetization, but observing it dynamically in a live celestial object is something entirely new. The Atlas anomaly therefore opens a window into the ancient conditions of planetary formation. Spectroscopic readings taken simultaneously revealed additional surprises. As the comet neared its closest approach to the Sun, NASA's ultraviolet and infrared sensors detected the emission of highly ionized oxygen and carbon lines at intensities not seen in comparable bodies. The energy distribution of these emissions did not correspond to thermal equilibrium, suggesting that localized electromagnetic processes were accelerating particles beyond what solar heating alone could achieve. This non-thermal excitation is consistent with the presence of field-aligned currents, streams of charged particles traveling along invisible magnetic pathways, linking the comet's surface to the solar wind. The anomaly also manifested visually. As the comet's coma expanded, it developed a bifurcated appearance, splitting into two lobes that rotated in synchrony. High-resolution imagery showed a faint, oscillating bridge of light between the two structures, a phenomenon that could be explained by plasma reconnection events. These are bursts of energy that occur when magnetic field lines snap and reform, releasing vast amounts of power in milliseconds. If Atlas was undergoing such events, it meant that its magnetic field was not only active, but dynamically interacting with the sun's own field, creating miniature auroral processes in the space around it. Such observations profoundly extend humanity's grasp of how small celestial bodies respond to the sun's magnetized plasma environment. Comets are usually treated as passive participants, frozen time capsules that merely react to solar radiation. Yet Atlas's perihelion anomaly portrays a much more complex relationship, an active, responsive object capable of generating feedback within the heliospheric medium. In practical terms, this could mean that the Sun-comet system operates more like a coupled circuit than a simple one-way flow of energy. NASA's instruments detected subtle radio emissions accompanying the light fluctuations, adding another layer of intrigue. These low-frequency signals, measured by the Parker Solar Probe and corroborated by ground-based observatories, bore the hallmarks of plasma wave interactions, oscillations that travel through charged gases under the influence of electromagnetic forces. The discovery raised the possibility that comets like Atlas might act as natural transmitters within the solar system, broadcasting signals shaped by their internal composition and motion through the solar wind. Studying these emissions could thus offer a new diagnostic tool for probing the physical state of cometary nuclei. The implications for heliophysics are immense. If comets can generate detectable electromagnetic signatures, they could serve as natural probes for mapping the solar wind's structure. Each comet would effectively trace the invisible scaffolding of the sun's influence, allowing scientists to reconstruct its shape and strength across different heliocentric distances. Atlas, in this context, becomes more than a single event. It becomes a prototype for understanding the deep coupling between celestial bodies and their space environments. The timing of the discovery added to its significance. NASA's ongoing studies of solar cycle 25 had already revealed an uptick in magnetic turbulence near the Sun, and the Atlas anomaly occurred during a period of heightened solar activity. This coincidence suggested that external conditions may have amplified the effects observed in the comet. In other words, the Sun's magnetic weather might have driven the resonance phenomena, pushing the comet's internal field to its limits. The feedback loop between these forces created a transient, observable signature, one that could only occur under a narrow set of cosmic circumstances. To understand the deeper physics, scientists turned to data from NASA's heliospheric imagers and coronagraphs. These instruments allowed researchers to trace the flow of ionized gas around the comet, mapping how solar wind particles were deflected and redirected. The data revealed an unexpectedly large magnetotail, a region of disturbed plasma extending millions of kilometers downstream. Within this tail, charged particles were organized into filaments and knots, behaving more like structures within a magnetosphere than a typical cometary outflow. Such organization implies self-consistent magnetic confinement, akin to what is seen in planetary environments like Earth's magnetotail or Jupiter's auroral zones. One particularly perplexing aspect of the anomaly involved the measured rotation rate of Atlas's core fragments. Observations showed that the spin rate oscillated periodically, increasing and decreasing in tandem with the light fluctuations. This behavior cannot be explained by simple mechanical torque from outgassing. It instead points to electromagnetic coupling between the nucleus and the solar field. Essentially, the comet appeared to spin up and slow down in response to variable magnetic stress, as though it were being tugged rhythmically by unseen forces. Such a phenomenon offers crucial insight into the dynamic relationship between matter and magnetic fields under solar influence. It also suggests that the interiors of comets may retain conductive pathways, channels of semi-metallic or magnetized material, that allow them to respond coherently to external fields. This concept aligns with the growing hypothesis that early solar system bodies were not purely inert clumps of ice and dust, but active participants in the electromagnetic environment of the protoplanetary disk. If Atlas preserves even a trace of that ancient structure, it may represent a living fossil of cosmic magnetism. NASA's analysis teams have emphasized that this finding could bridge gaps between planetary science, plasma physics, and astrophysics. By examining how comets behave under solar stress, researchers gain insights into both small-scale material properties and large-scale field interactions. The Atlas anomaly effectively blurs the line between solid-body physics and space plasma dynamics. For decades, these fields were treated separately. Now they converge in the shimmering wake of a dying comet. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on NASA's new Atlas Perihelion Anomaly discovery? We want to hear from you. Thank you for watching, and see you next time.